273 kelvins.
0.15.
Yeah.
Yeah, but when we do the math, 100 Celsius equals 373.
Mm-hmm. 0.15.
Yeah. So that means 1 centigrade equals 1 Kelvin.
Yeah, that's right.
But 0.
Kelvin and centigrade are the same thing. Some people call it centigrade because it's based on centid, 100, 0 to 100 for water. That's why it's called centigrade, because there are 100 levels between freezing and boiling. But yeah, you're right. I mean, yes, 100 degrees Celsius is 373.15 kelvins.
Hey, where did you go for Concordia?
Where, huh?
Did you go to Concordia?
Yeah.
Okay, where was that?
In Chicago.
Okay, that.
Concordia River Forest is now Concordia, Chicago.
Yeah. Okay, because I visited the one in Ann Arbor.
Mm-hmm.
It was so tiny.
It's tiny, yeah.
And like the professor I talked to was basically saying, "Go to Hope College." I'm like, okay, not going here.
My college roommate teaches there now.
What?
My college roommate teaches at Ann Arbor.
Oh,
He's the
really?
director. Yeah.
Cool.
All right. Anyway, so 363, 10A. You didn't have any problems with that, right? That's the stuff we did during class yesterday.
Oh, yeah.
Okay. Anyone have any questions about any of those?
No.
Okay, good. Just real quick on number 5 there, liquid nitrogen is used to cool substances to very low temperatures. Express the boiling point, which is 77.34 kelvins at 1 atmosphere pressure. Why do you have to specify the atmospheres of pressure?
Because it matters.
Yeah, why does it matter? What changes about it?
The atmosphere can change the amount of temperature.
And how does that change the boiling point of nitrogen?
It would make it. I mean, if you're in a higher atmosphere, then it would make it less boiling.
By higher atmosphere, you mean thicker or more pressure?
Less pressure.
Oh, you mean
Like
higher altitude?
higher,
Okay.
yeah.
Higher altitude would be less pressure, and then what would happen to the boiling point?
It would decrease. No, increase.
No, you're right. It would decrease. It wouldn't have to get up that high to boil.
Okay.
And then you're saying taking longer to boil. I think you're thinking if the pressure's higher, right? If the pressure's higher, it takes longer to boil because you have to achieve more.
Oh, that makes more sense.
Pressure from heat, I guess, before it can escape the pot or whatever. Now, nitrogen, I don't care what the temperature is. Here on Earth, nitrogen is going to boil anywhere you leave liquid nitrogen open to the atmosphere. Because 77.34 kelvins is what Fahrenheit?
Negative. Wait.
You have it, right?
5. Are we talking about the yesterday number 5 or today number 5?
The F for number 5. What? How many degrees Fahrenheit?
320.46.
Negative, right?
Yeah.
Yeah, that's a big difference, right? Negative. So the temperature on Earth is never going to be negative 320 no matter where you are, okay? So nitrogen is always going to boil as soon as it's exposed to the air. Think about water. A lot of times on like the side of a box for baking a cake or making a box dinner or something, they'll have high altitude cooking directions. You guys know what I'm talking about?
Mm-hmm.
What do those usually, do you know what the difference usually is with those? What's different from cooking it at sea level? What's different about the directions?
Time it takes.
The time? Right. What do you think about the time?
It would take less
Well,
time.
the higher you are.
It's going to take longer, actually, yeah.
But, what?
I have a great example I'll tell you in a second.
Okay.
It's going to take longer.
Longer they cook at a higher altitude?
Yes.
That's weird.
But also, a lot of times, you have to add more water at higher altitude. Or more moisture. Why would that
Because
be?
it boils off quicker?
Yeah, exactly. Boils off, saps off.
Oh, okay.
I have an example. In high school, my family took a camping trip to the Rockies. So one night we were boiling noodles over a campfire. Okay? Boiling point of water, normally we're used to 212 Fahrenheit around here, right? We're pretty close to sea level. Well, up there, the water started boiling way before 212. So we put the noodles in, cook them for 8 minutes or whatever, take them out. They're nowhere near done. We're like, what the heck? We put them in, leave them a couple minutes longer, they're still not done. Well, at home, they'd be like disintegrating by now. Why are they still not done?
Is it because the temperature wasn't the same as it would be?
Yeah, it was boiling at a lower temperature, and so the temperature wasn't high enough to cook the noodles as fast, even though the water was still boiling.
That's really weird.
If you were to have a closed system, like imagine a bowl of water in a glass box, and you were to take all the air out of the box, the water would boil at room temperature. Because if it's a vacuum, that liquid instinctively that fluid wants to fill the entire space. Okay? So regardless of temperature, if there's no pressure, it's going to jump to fill everything.
Oh, that is so cool.
So yeah, that partly explains then what happens with high altitude then. So since everything boils faster, or sooner, I should say, at a lower temperature, it takes longer to cook because you're not using the same amount of heat as you would down here.
Yeah.
Speaking of heat, all right, now the section review questions. So, number 1, and you guys did these for today, right?
Yeah.
Okay, so which one of those pictures, A, B, or C, what order should they be in?
C-A-B.
C, A, B, right.
Cab.
And you can tell by the outlines. Now, how come the blue ones, shouldn't blue be cold and red be hot? So why do the blue ones have longer trails?
They have more kinetic energy.
Yeah. So what's their temperature?
Warmer.
They're actually warmer than the red ones.
Okay.
Color doesn't matter here. And actually, did we talk about this the other day? The hot and cold in your faucets, that's actually wrong. It should be blue hot, red cold. Because when things, you know how things glow red hot? Well, if they get hotter yet, they turn white hot, but they turn blue hot. Blue is the hottest, actually. We think of blue as being cold and red as being hot because of...
Do we associate blue with water?
Exactly, yeah. We associate blue with water and ice and things like that.
Oh, that's
So-
interesting.
Yeah, it's a little bit backwards. Think of flames. If you watch the flame on the burner at home, it's bluest where it first comes out, where it's hottest. Yeah. Okay, number 2. Hot copper pan is dropped in a tub of water. If the water's temperature rises, what happens to the temperature of the pan?
It goes down.
Right. How will we know when they reach thermal equilibrium?
There's no more steam.
When they're the same temperature.
Yeah, simple as that. When there's no more when they're at the same temperature.
Oh.
There's
I
gonna be
was
steam
thinking
right when you
visually.
drop it in, but once it's submerged, there's probably not gonna be much steam anymore.
Okay.
You know?
Yeah.
That one, it's easy to think too hard. Thermal equilibrium, well, same temperature. That's what thermal equilibrium means. So yeah, that's all it is. All right, number 3. Oxygen condenses into a liquid from a gas at 90 kelvins. To what temperature does this correspond on? We'll skip that one because you guys know how to convert. Make sure both reactions are negative. Number 4.
Kind of the same.
Yeah, same thing.
So is 4. Oh, yeah.
So on to 5. I made popcorn last night. Just to test this. No, I wasn't even thinking about this question when I made popcorn. I was just hungry. I made a spicy Orville Redenbacher's spicy nacho popcorn.
Oh, that's interesting.
Horrible.
It wasn't that bad. I got it on clearance because I guess no one wanted it. It wasn't too bad. It could use more cheese.
Yeah.
Yeah, it doesn't sound that great.
Anyway, it still popped the same way regular popcorn does.
That's good.
So what happens during popcorn popping? Which of those things do you think happens?
A and C.
Okay, Sue, what did you say?
Kinetic energy?
Kinetic energy increases, yes, definitely. That's C. Why?
Temperature rising.
Mm-hmm.
And so the molecules are moving faster.
Yeah. It has to do.
So like the potential, wait.
This is the it's the ideal gas law. The microwaves or whatever is heating the popcorn increase the temperature, and then that increases the pressure also. Okay? Because the volume is constrained, it's a kernel. The volume can't change, right?
Oh, I see.
So since temperature goes up, something over here has to go up.
But the
One thing it
volume
can't is
does
pressure.
change in the kernels.
What'd you say?
The volume, it changes.
It will change when it pops, right? When it explodes, when this volume can no longer withstand the pressure because the pressure's too high.
Oh, that's cool.
And that's why it pops. And it's because of the water inside. There's water inside it, and that water is expanding because it's getting hotter and hotter, pushing out against the edges. Eventually, it finds a weak spot and pop. There's your popcorn.
That's interesting.
So, number 6. Which of the, okay, and what we're assuming here with this hot plate is that the popcorn thing has been on the hot plate for a decent amount of time, long enough to warm up the pot as well.
Well, an A.
What'd you say?
I wrote down A.
A is true. Thermal equilibrium. So we're thinking of things in the same temperature. The hot plate and the glass pot, yes, if they've been on, unless you just put the glass pot on, if they've been on for a while, then yeah, they're going to be equal.
Wouldn't that be the only thing though? Because otherwise the popcorn wouldn't be popping if they were the same temperature.
Yeah, I thought it
What do
would
you
be too.
They're heating up, and when they get like that, do they ever reach the same temperature?
But
The
it's still
popcorn?
kernel when it's
Kernel,
hot.
the kernel,
It's
and
still, I
the
mean, it doesn't change it.
Well, they're all going to be the same temperature, just going to pop at different temperatures. They're all going to increase in temperature at about the same rate. Well, yeah, the popcorn, the kernels at the bottom are probably going to get hotter first. Is that what you mean? They're not all going to be the same?
No, like-
if they were going to be in thermal equilibrium.
The kernels?
Yeah.
They would be popped already.
Not
But not necessarily.
I mean,
If it was room temperature and it was still.
yeah, before I put them, if I got all the kernels sitting in a bag and I haven't put them in a container yet, they're still in thermal equilibrium there, right?
Yeah.
So,
Yeah, this is the hot oil.
But
right,
it doesn't
so
really specify how hot it is.
it doesn't specify how hot, no, but what do you know about oil? If you get burned with oil, does it hurt?
Yeah, it sucks.
And it like stays on for a while, like it keeps burning, right?
Yeah.
Because oil has a high specific heat capacity, it holds a lot of energy. So chances are, if the oil's hot, the popcorn is also hot with it. So technically B would also be true. Those are in equilibrium. Because the oil is what helps to get the kernels all at the same temperature as the
I
popcorn.
was just thinking like it wasn't going to be the same temperature because they would no longer be like a little kernel, like because then it pops into the big puffy white thing, and that's not going to be the same temperature.
Why not?
I just don't think it is.
Well, as long as if the pot's closed and the heat can't escape, then I think it is until
And
you open
that's
it
why
up.
it burns and stuff. Keep it in there too long. Right?
You release it. What did you say?
Like, that's why it burns if you keep it in too long. It's because
Yeah.
the temperature keeps in.
Yeah, what's happening there, AJ, is all of a sudden volume starts to go up too because the temperature went up enough to exceed the pressure it can withstand. So volume goes up too. But there's nothing that decreased temperature, right? Technically. I mean, you could argue that, okay, well, the popping expended kinetic energy, so maybe the temperature went down a tiny bit. You could argue that. I give you that. Because anytime a molecule moves, it's using part of its energy. If it uses its kinetic energy, then it's decreasing the temperature. Alright, let's go on. We talked a little about heat yesterday and about internal energy. So, this is pretty basic stuff. 10.2, it says, well, let's just look at I think we just look at the headings of each section and get through it that way. So 365, energy is transferred between substances as heat. Yeah, right, makes sense. Can you guys give an example of where you transferred energy to anything this morning? Did you use heat at all to transfer energy?
Using my car.
What'd you say?
Like driving my car.
Okay. Did you take a shower this morning?
Yes.
Dry your hair afterward?
No.
Okay. Anyone use a hair dryer this morning? Sue, alright. So tell me about hair dryers and heat.
I will transfer heat into it so it can dry off.
Why does heat dry faster? Why does heat make water dry?
Water's getting more kinetic
It's evaporated.
energy.
Right, it's getting closer to the energy necessary to evaporate. The heat of evaporation.
Isn't more the
Heat of
motion,
vaporization.
like the air blowing though? That makes it
That
dry.
makes a huge difference too, yeah. I mean, you can put, I remember my mom's really into like all this prairie stuff, so Little House on the Prairie was like her favorite show and everything. And in the books, like they will actually hang up clothes on the clothesline in winter and freeze dry them.
Oh yeah.
And
How
so
does that anymore?
I've
they
done
like
that
freeze.
with a t-shirt.
Yeah.
I had to use it quickly, so I hung it outside the winter and froze, and
And
then
they
dried out.
yeah, they freeze and get solid, but when you bring them back in, they're dry.
That's so weird.
So I mean, yeah, the wind makes a big difference.
That's so cool.
But heat will always make things dry faster because you're closer to the heat of vaporization, closer to what the water needs to change phases.
Oh, that did happen to my hair a lot, actually. In the winter when I would go out after my shower or whatever, it would freeze and just crack.
Like you take you take a washcloth, a damp washcloth, and swing it around in the air. After a while, it starts to feel cool, right? No?
Wait, so we might washcloth?
Do an example. Yeah, or something. Well, I'm not saying in the shower, but
Oh,
It's
yeah.
like you touch a washcloth and it's gonna...
I have an instrument here
Oh,
called the swing thermometer. And so this thing has two thermometers, which are at equal temperatures. This one's got a little piece of cloth wrapped around it. If I dip this cloth in water and I swing it around through the wind, creating wind, after a couple minutes, this temperature will start to drop. Okay? This one will remain the same. The dry bulb will remain the same. The wet bulb one drops. Why?
Because it gets cooler.
Why?
But, I don't know.
Remember we talked about sticking your hand out the window? You guys remember that?
Yeah.
Say it louder, AJ.
It takes longer for the water to evaporate off the cloth.
But it is evaporating, right?
Yeah.
So as it evaporates, what does it need to evaporate? It needs heat, right? Where's it going to get that heat from? The air, but it's also going to take some heat from what it's touching, conduction. It's going to take some heat from the thermometer. So it's going to decrease the amount of heat in there, so the mercury is going to sink a little bit. And so it drops. We'll try it out here.
This one?
Don't need ice water, doesn't matter what temperature. It will feel cold after a couple minutes anyway. Actually, we want room temperature water. This water's been sitting here for 2 days. So, and this proves the point because you know the water's not colder than the air. It's the same temperature. So both of these right now read 71 degrees here. I'll show them to you.
I feel like you didn't write that.
What? You're correct. Well, here, take it. Okay. I had Mick write that because I was back there trying to adjust the focus and everything.
Alright, Sue, give it a whirl.
Just swing it around. There you go. Mix and get sprayed a little bit. Yeah, I keep it going for a couple minutes. We're going to keep talking while you do that. If you get
Come
tired,
on,
pass
Sue.
it around.
Yeah.
Just don't launch one
Get a
out.
workout.
Yeah, if you launch one, someone will get mercury poisoning, so be careful.
Now, is that real mercury?
It is, but there's a very small amount in there. It's not going to hurt anyone. I mean, as long as you wash your hands or whatever afterward.
Yeah, don't drink it. You have to keep it going, Sue, though. You can't pass it up.
Yeah, don't stop. If
It's
you want to
okay.
pass it around, that's fine.
Yeah. You can do it for at least a little while.
Okay, so in my opinion, all these dark boldface headings in 10.2 are no-brainers, right? Energy is transferred between substances as heat. Duh, we know that. Turn the page, 366. The transfer of energy as heat alters an object's temperature. Duh again, right? Of course it does. Yeah, keep going fast. There you go. 367. Heat has the units of energy. We talked about that yesterday. Heat is measured in joules. And here, this explains, what was our variable for heat again? What's our variable for heat?
Heat.
3, is it gonna fly
Q.
off?
Q.
There's a.
And what was our variable for internal energy?
You.
U.
Who?
So, what happens is the amount of internal energy, the amount the internal energy changes is related to how much heat is added or taken away. That should make sense to you. These are both measured in joules.
I put a little thing on the U so we don't get confused with volume.
Will do. So heat is the transfer, it's just the transfer of internal energy. It's the avenue through which internal energy is transferred. It's transferred as heat. How we doing? What's the what one say?
65.
Good. Keep going. Go a little more farther.
67.
Yeah, the other one will go down a little bit just because, well, that's not the most accurate thing. I haven't taped together, so you're basically doing a centrifuge, so that might be. We gotta check and make sure the temperature's.
Yeah. The other thing. Do you think the centripetal force affects it at all?
That's what I was thinking.
Yeah, it doesn't affect it enough.
Okay.
It affects the.
You would have to
sliding
be
down
whipping
against
the snot out of
paper.
the thing.
Yes. Yeah.
Like to actually affect the amount of mercury in there, if that makes sense.
To affect the mercury going back down.
Because you'd have to condense the mercury.
Oh.
You know, and in order to condense, the mercury is expanding and contracting because of what? The density of the mercury changes?
Changes.
What? Temperature. But temperature has a far greater effect than
Yeah, it
does.
worked off.
Grab
Awesome.
that.
It certainly does change. That's what changes the
Right.
ground look different.
Then
So
does
let's do the temperature.
centripetal force. Good. Come on, come on. Every time we stop, it rises.
It should be about. It should be pretty close now.
Yeah.
All right, so let me see it, and I'll have you feel the bulb, and you should see that it feels a little cooler now. Yeah. Okay. So we have 14 degrees Celsius versus 21 degrees Celsius.
Whoa.
Look at the difference, and feel the wet bulb on your way.
Hurry though.
Yeah, hurry before the.
Every time you feel it, it's going to turn back.
And so, because of that, what will we use that instrument for? What do you think it's for? It's an actual weather instrument. Huh?
Barometer?
No, not barometric pressure.
I know.
Good.
What did we create? An artificial what?
Wind.
Did we?
I mean, yeah.
Of course.
Yeah, instead of the air moving
Yeah.
against that, we move that against the air.
We created an artificial wind, right?
Yeah.
Think about what does wind affect. Well, okay, so what variables were in here? We created an artificial wind. What do we measure? What? Temperature. Do those relate at all? Wind and temperature.
Yes.
Wind chill.
What?
Wind chill.
No, you're way off.
Uh-oh.
But I mean,
That's the only.
Way off. Why?
okay.
That's what I thought.
No, I mean, I can see where you're getting that from
No?
because we are creating wind, but I mean,
That's wrong?
It's an improper measurement because one's wet, one's dry. No, it has to do with. Okay, think about the clothes drying and the clothesline again. Do they dry faster in the rain or in the sun?
The sun.
Why? Because the air is drier. That measures dryness. That measures humidity in the air. Okay? Because the rate at which the water evaporates will change based on how much humidity is already in the air. If the air is already 100%, if I stand outside in the rain, is any water going to evaporate? No, because the water is already 100% saturation. Okay, rain's coming down, so the water is 100% humidity because the air is 100% humidity. So since it can't come down, it's not going to change. So the closer two temperatures are, the closer you are to 100% humidity.
I didn't factor in moisture,
Got it.
which is the largest factor.
Yeah, exactly.
That's the only one that's not controlled, or that's not controlled. That's the only one that's not consistent in the two.
Yeah. So think about if it is the middle of winter inside, what do you think would happen to the wet bulb?
What?
If we did that same thing in the middle of winter, like in January, in this room,
Colder.
the wet bulb would get colder, right? Because as you swing it around, the air is much less moisture in the winter because you're taking low moisture outer air and heating it, baking it, and the moisture is not in there. So it evaporates faster. The faster it evaporates, the cooler that thing gets because it's sapping more heat. It's taking more heat away from the bulb. So by knowing that, by 14 and 21, there's a chart that I can use and I can tell you the humidity in this room. And the humidity is about 44% right now. So there we go, that's what it's used for. It's called a sling psychrometer. Psychrometers measure humidity and you sling it around. Anyway, so that kind of, but it's all based on heat. Heat due to evaporation. Okay? Evaporation requires heat for it to happen. Okay, so look at page 368, conservation of energy. We talked about that yesterday a little bit. Look at the form they have. It's a little different from how Mr. Ernst wrote it yesterday. He wrote this.
I wrote both.
Yeah.
Oh, you did? You wrote the change in also?
Boom.
So you know how we get change in, obviously, right? We move all this over. It's PEF minus PEI, so it becomes change in plus change in plus change in equals nothing. Okay, we move it all over one side. Okay? Conservation of energy. So anything non-movement related, macro movement is going to go into internal energy right now. Change in internal energy is 0 because energy is neither.
Great.
Good. So, we just talked about water, that dry bulb. What was that water doing? It was evaporating, right? That is called a change in. Where's water? It's changing between liquid and gas, right? It's going to a vapor. Vapor is a gas. So what changed about the water? It changed its state of matter, right? What's another word for the state of matter?
Potential.
What'd you say, AJ?
Phase.
Phase.
Oh.
Any change of phase requires Q. Requires the transfer of energy. Okay? Which is heat. Heat is the transfer of energy. It requires that. Now, does that mean that everything needs heat to change phase? No. Sometimes it needs to lose heat. Okay? It needs to either gain or lose. So if we go from liquid water, let's think about water here. If it goes from a liquid to a gas, what did it need to get there?
Q.
It needed to add Q, right? What if it wants to go from a liquid to a solid?
It needs a lack of heat.
Right, it needs to lose heat, exactly. Negative Q. It needs to lose heat. Where does the heat go? Somewhere else, to something else. When you freeze ice cubes, and you guys have the old-fashioned kind of freezer, you got to make your own ice cubes? Or do you have automatic ice maker? Okay. I have the old-fashioned kind. I hate it. I want an automatic one. But okay. So what?
Splurge.
I'll splurge when my fridge dies. Until then, I won't splurge.
Yeah.
All right. So you put water in the ice cube tray. You stick it in the freezer. What does the freezer do? It freezes things, right? That's why it's called a freezer.
Wow.
So what's
Wait a
happening?
second.
Here's before, and here's after.
Actually,
It would be higher though.
You're right, it would be higher. I was going more with a straight line here, showing that now it's rigid and not moving around.
Why is it higher?
Because
to
it.
expand it.
Yeah.
Why?
Because that's what ice does.
What?
That's what water does.
What else does that?
The density decreases.
What, AJ?
Nothing.
Are you sure?
Yeah.
Good.
Alright, so so before, think about the temperature of the water versus the temperature of the freezer. Okay, so you're inside the freezer. Water temperature, give me an estimate of what you think it might be when you take it out of the faucet and put it in that tray.
75.
Okay, so you're taking room temperature water. That's fine. We'll do that.
60. I'd go 60.
Can we use Celsius, actually?
Oh.
Since we're in physics. Nick, what do you think?
25.
25?
25.
That's pretty warm, but okay.
That's warm.
That'd be what, about 80 degrees, you think?
That's my room temperature.
What? That's your room
that's
temperature.
That's true, that's true. That's mixed room temperature,
That's
yeah.
hot.
Thailand, yeah, okay.
That's terrible.
Aye. See, I told you guys. He's weird.
You drink 80-degree water?
Who does? Oh, man. When I lived in Houston, it was horrible. The tap water never came out cold. It was always warm. It was disgusting. Because
Yeah.
I grew up in Milwaukee and, went to college in Chicago.
Rivers.
Huh?
Milwaukee is the land, that's what it means in Indian.
Land of what?
Many rivers.
That's correct, yes. So, you know, I'm used to nice ice cold water coming out of the tap, especially in winter. Well, in Houston, number one, it never frosts, so all the pipes are exposed, they're above the ground, which means they get baked by the sun. Even the cold water. The cold water comes out 80 degrees in the summer.
That's awful.
Yeah, it's not cold. You gotta chill before it can do anything. So, yeah, it sucks. Because it has too much heat. Alright, what's the temperature of the freezer?
Negative.
Well, if it's freezing.
33, not 32.
No, most
We
freezers.
want Celsius.
Yeah, that's really hot.
0.
Vic, what?
Negative 7.
Most freezers are around 0 degrees Fahrenheit.
Yes, 0 degrees Fahrenheit. So what would that be Celsius?
Negative 8, 7, something like that.
About negative 15. No,
15?
negative 8.
Yeah.
18.
No.
18.
4. What?
Negative 18.
0 Fahrenheit.
That
Oh, do we have to do this?
Yeah, he's right. He's
Alright,
right.
let's
He's
do
much.
it.
Yeah, I think it's not that much. Like,
I don't think it's that cold though.
Negative 32 divided by 9 is a little less than 4 times 5 around 18. Negative 18.
It's warm.
really?
You should have known that, Mick and Sue.
I thought it's like negative
Oh,
7.
we clicked our calculator.
No,
What?
I'm sorry.
I'm like, what the heck? We just went through this.
Negative 10.
Or 15, like.
We have about negative 18.
My freezer is at negative 18. My freezer is 0 degrees Fahrenheit.
Yeah, the good freezers are at negative 18. Bad
Yeah, my
ones are
freezer's
negative
good.
What?
I'm not talking about my crappy fridge that doesn't have an automatic ice maker. I'm talking about my deep freezer in the basement. That's at 0
Oh,
degrees.
you have a deep freezer.
10. He's a baller.
It can go down to negative 10 Fahrenheit.
Mr. Gottschalk's starting to be like Mr. Schoenlauf.
I buy nice appliances for cheap, yeah. Anyway, okay, afterward, what's the temperature of the water? What's the temperature of the freezer?
They're both the same.
What do you think they are?
Negative 18.
Yeah.
What? Okay.
Because the power of the electricity or whatever is so
But
great that
wait,
it doesn't really matter.
The freezer thing keeps sucking out.
Yeah, it's always at its.
So.
Science never sucks.
Yeah, science never sucks.
It may push and pull,
Not mine.
but it'll never suck.
What's wrong with this? If it's a closed system, what's wrong with that?
It should be a little
the
warmer
freezer
then,
should
right?
go up.
Yeah, we didn't conserve energy if this is a closed system, right?
It's not.
Because the energy of the water had to go somewhere. There must be some other substance where it went if it's not accounted for in here. If these were to equalize, maybe they'd equalize to somewhere around, I don't know, -1, -2C, something like that.
Really? That much?
No, it'd probably be more. It'd probably be above because they're 25 and -18, so it'd probably be, what's the average
Yeah,
of
but
25
I
and
mean, are you talking about like a
-18?
small
3.5
fridge or a
degrees.
big fridge? Because I mean,
Gotta be at
it
least
kind of
0,
depends, doesn't it?
Yeah.
Okay, well, yeah, you're right. It depends. It depends on the amount of air and the amount of water.
Otherwise it wouldn't be frozen if it wasn't 0, would it?
It wouldn't be frozen if what? Right.
You said it's gotta it would be around 3, but then.
Yeah, if we consider equal amounts of water, equal masses of water and air,
Because I
now
mean,
air's not heavy.
I just don't think it would change that much.
It
Well,
wouldn't change because it's a
yeah,
freezer.
it honestly wouldn't because air is a poor transfer of heat. Okay? That's why when the air is cold outside, you can stick your hand out there and it's just fine. You stick your hand in ice cold water and you want to take it out right away, right? Because there's so much heat being taken from your hand.
Yeah.
It doesn't get taken as quickly from outside.
I noticed that with the same thing, like with the sauna, it's like 200 degrees in there,
Mm-hmm.
and you're like sweating or whatever, but it's fine, and then you go in up like 100 Fahrenheit.
Let's go with 130.
It was
Yeah.
195.
200's a bit excessive.
No, you
It's
sit
hot.
it's not 130, it's like 1.
It can't be more than 150.
Really?
No, gosh, in a
Oh.
sauna?
That's
Oh, a
what-
sauna. I'm talking about a hot
I'm
tub.
thinking steam room. Oh, hot tub.
And if you sit in a hot tub in the dead of winter, you're like 110,
107.
107 is probably more like it in
Yeah.
the water. And your hair, if you spike it up, it'll freeze. Like standing
Really?
straight up. Yeah.
It's
And it
so
doesn't even have to be that cold. Just as long as it's below freezing outside, if you sit in the hot tub and you take your hair, it's pretty cool. We did it with this girl who had like really long hair. and we all held a strand up, and so she had like a mohawk the size. It was crazy. It was fun. My buddy had a hot tub when we were in high school, so that's yeah.
It's
But,
fun.
All right. You guys are coming up with good stuff here. So what matters? What matters with the transfer of heat? What matters? Initial final temperature, final temperature, right? Temperature mattered. What else did you say mattered? We talked about the size, the amounts. Okay.
What else matters?
Closed system or
What's that?
not? Closed system.
Closed system? Yeah, of
It
course.
doesn't matter. Yeah.
Yeah. What else?
Little C.
What?
Little C.
Little c, Sue
Oh,
says. What is
What's
little
little
c?
c?
In the equations?
In the equation, that's what we're asking. Yeah,
Yeah.
what is little?
Yeah, down
Yeah, I know. What is it?
it's
All right. So we put. Hold on. We put.
The mass.
Let me think.
You gotta change
We put a bottle of vodka in the freezer, and we put a bottle of water in the freezer. Which one freezes first? Depending. Why?
Because the vodka takes forever.
Vodka
It's
won't.
slush.
Regular vodka won't freeze because
At what?
at the same temperature. Because
I don't know.
They're gonna lower.
what is in vodka?
Alcohol.
Alcohol is about 40% or 50% or whatever it is, and alcohol has apparently it has a lower freezing temperature than does water.
It also has a lower evaporation point. That's why. Okay, here's some alcohol. Anything
Or
left?
not.
There we go. That's fine.
That puts it right there.
And here's some water. If I smear this around, and I smear this around, what disappears first?
The alcohol.
Yeah, it's got a lower evaporation point too. Everything's lower for alcohol.
Does that make sense?
It didn't need as much heat from the atmosphere or the table to jump, to change phases.
So the substance's freezing/boiling point, or just generally we can say what substance you're talking about, and what that has to do with is the small c. Anybody remember what the small c stands for? Water has a very high one of these.
Calorie?
It's a 3-word thing.
These two, this is what we've referred to it so far. Water has a very high blank. This is why Lake Michigan rarely, if ever, freezes over completely. What? Say it out loud.
capacity.
That's the C word, is capacity. That's the one we haven't used thus far.
There's something heat.
Water something heat. And this is blank for each substance.
It depends on the substance.
Specific.
Okay.
Specific heat capacity. We usually just call it specific heat. But water's specific heat is very high. It is one of the highest in of the substances that we will work with on a regular basis. If you flip to...
So, wait, hold on 1 second. So
Okay.
heat transfer is dependent on these 3 things, right? That becomes our equation. All right, now flip Mr. Ernst.
372. That's just a short list of a few of reasonably common substances that you know of. It's kind of striking. Look at how much higher water is than copper and aluminum and glass and gold, etc. Does glass have low or high or somewhere in the middle?
Glass is lower.
Yeah, glass is lower, which is that good or bad for us?
I really wish air was on here.
It's bad.
Yeah. What?
That's kind of bad for us that glass is a low specific heat. We kind of wish it had a higher one.
What?
Because then
Glass and-
we talk about this building being a sieve, right?
Oh, I see.
You know, those windows, those huge windows.
Because if, it wouldn't matter as much. You guys know
Well,
why...
that's why you want double pane windows.
Yeah,
You know.
Nah, you spoiled my...
Sorry.
Why this window's awful. Come and touch this window. Come. What? Yeah, it's pretty chilly. If you you guys have, does anybody know if they have newer windows at your house?
We have
Yeah.
like, yeah.
You have new? If you touch your window, I guarantee it would be warmer than on this side. It would be much warmer than this window.
Yeah.
Because the difference between this window and what Mr. Gottschalk said, they make double pane now, they make triple pane, they make quadruple pane.
Are you serious?
Yeah.
So there's air in between.
It's
and
not,
so the
well,
air's
it's not
buffer.
air actually.
It's some kind of gas. Right?
Argon.
Yeah.
And
Argon
that means
gas
it
goes
doesn't
inside.
transfer then?
And that acts as an,
Buffer.
what is science? An insulator.
Yeah.
And as Mr. Gottschalk said, air does not transfer heat well. We would call air an insulator rather than a
Transfer.
Conductor.
conductor. You learn those terms, you know, in 5th grade, right? What are good conductors generally?
Copper.
Conduction is what?
And copper.
What
is
are
a-
good conductors? Just one word I'm looking for.
Metal.
Metals are generally speaking
Now,
good
yeah, you're thinking more of
conductors.
electricity, but we're talking about heat. There's a difference there. Copper's good at both.
Yeah.
Yeah.
I mean, that's why they put the copper lining on the bottom.
Yeah, honestly, gold and silver are better conductors, but they're too precious and too expensive.
Exactly.
In the 60s and 70s, they started using aluminum because aluminum's a decent conductor also, because it's a lot cheaper than copper, still is.
Yeah.
And there were these planes. The A380 Airbus, one of the big new planes, was built with aluminum wiring, in some places copper in others. And that caused a huge problem because the electricity running through there would overheat when it got to the aluminum and cause fires and, you know, wire insulation melting. They don't use aluminum wire anywhere anymore because it doesn't work as well for electricity.
Didn't they used to make crowns out of aluminum because they're so hard? Like,
Make what?
it was crowns, like,
I don't know.
because
What
like,
did you
I
say?
don't have much experience with
because
crowns.
someone, I can't remember who told me this, but someone told me that aluminum was a lot more expensive because they couldn't put it into like what we have now very easily. Like we couldn't. I don't know. But someone told me that they used to make aluminum crowns.
You're talking about like a
Yeah.
king's crown. I don't know. I thought they used to make it gold.
Yeah,
Gold's
but like
what I
I mean, it used to be a lot more
I have a
valuable.
diamond crown.
Okay. Yeah.
So what kind of
yeah.
crown is
A
it?
diamond one.
You have a Burger King one?
A solid diamond.
Paper?
Yeah.
All right.
Nice.
So what do you think the P is for here? That doesn't. I mean, this is the variable for, or the constant, I should say, for the substance you're talking about, specific heat capacity. What's that P for? The P in capacity? The P in specific? Doesn't make much sense, right?
No.
What does the P mean?
Passing.
What is all this dependent on? What do we say? What's the difference between high altitude cooking and here?
Pressure.
Pressure. This is based on a constant pressure. Okay? If it's not a constant pressure, these are not. This equation doesn't quite hold true. Okay? Because otherwise, it's not a closed system. So, all right. Let's see. For Monday, read 10.3.
You want
I want your homework. Yes. Did you do page 370 yet? 10b. I don't think you did.
no.
All right. Do 10b for Monday and read all of section 10.3.
10B or not 10B?
10b.
That is the question.
Wow.
10.3 is a long section, so
10-3 or not 10B?
read it well.
What is that one for?
Crack me up. Can you turn off the camera, please, while you're over here?
Yes, sir.
Have a good weekend. You said you can't make it tomorrow or on Sunday?
No.
That sucks.
Yeah, sorry.
Yes, Sue.
Two?
Oh, Mr. E, not Mr. G. Okay. I never know because everyone calls me Mr. E too.
No,
Yeah.
Yes, Sue?